Welcome to Thought Frontier.
All right, buckle up, everybody, because today we are going deep on time crystals.
Time crystals.
You know, you sent us a ton of really interesting articles and research on this.
Yeah.
This is going to be a wild one.
It is.
Okay, before we get too far, let's just sort of like set the stage.
Yeah.
Most people, when they think of a crystal, they think of like a diamond or, like a snowflake, something with a repeating structure, like in space.
Right.
But a time crystal, these things repeat in time. Like,
Yeah.
how is that even possible?
So imagine like a system that just never winds down.
Okay.
It never loses its order.
Huh.
So it's like a perpetual motion machine, but it's totally allowed by the laws of physics.
Okay.
So that's what's so mind-blowing about time crystals.
Okay.
They seem to defy, the normal rules of entropy.
Entropy. Now, remind me what entropy is again.
Basically, the idea that everything in the universe tends to move towards disorder over time. Like, if you leave a cup of coffee on the table,
Yeah.
it eventually cools down.
Right.
A pendulum eventually stops swinging.
Right.
Things lose energy.
Yeah.
And they become less organized.
Got it. Okay. So time crystals, they don't do that.
Exactly. They stay organized and keep oscillating, even in their lowest energy state.
Wow.
It's like they have this internal clock that keeps ticking without needing to be wound up.
So how does that even work? I mean, like, doesn't that break some sort of law of physics?
So it's not about breaking the laws. It's about bending them, in a way.
Okay.
And they do this because of a quantum principle called many-object localization.
Many object what?
Localization.
Okay.
And imagine a bunch of atoms all doing their own thing, but somehow they're all still in sync.
Okay. I'm going to need you to unpack that a little bit. That's a lot.
Okay, so think of it like a group of dancers.
Right.
Each dancer has their own, individual steps.
Yeah.
But they're all choreographed to move together in a pattern.
Got it.
If one dancer gets bumped, it doesn't mess up the whole routine.
Right. Right.
Because the other dancers keep going.
So even if one part of the time crystal is disturbed, it doesn't affect the overall oscillation.
Precisely. It's like each atom is doing its own thing, but there's this underlying order that keeps the whole system ticking in perfect time.
So they never lose their rhythm.
Theoretically, yes.
They just keep on ticking.
Now, observing them is a bit tricky because they're inherently quantum objects,
Right.
meaning they behave in ways that classical physics just can't explain.
Yeah, quantum mechanics, always a little bit of a head scratcher.
It is. And one of the big players here is the Heisenberg uncertainty principle, which basically says we can't know both the position and momentum of a particle with perfect accuracy.
So it's kind of like trying to like pin down a hummingbird in flight.
Exactly.
Yeah.
And when we observe a time crystal, we kind of freeze its quantum state, disrupting its natural behavior.
So it changes it.
It does. And this limits how long we can observe them before they essentially break down.
Okay.
But scientists are getting better at observing them for longer periods.
So even though they theoretically last forever, in reality, we can only observe them for a limited time.
Right. But there was this incredible experiment where researchers linked two time crystals together inside superfluid helium-3.
Superfluid what?
Helium-3, which is, supercooled helium.
Okay.
And they observed these linked crystals for a record-breaking 17 minutes.
17 minutes. That's amazing. I've even read about one lasting for like 40 minutes. I mean, it seems like the field is progressing really fast. But I have to ask, like, why all the fuss about time crystals? What makes them so important?
Well, time crystals have the potential to completely revolutionize the world of quantum computing.
Quantum computing, now we're talking. Everyone's buzzing about it, but I'm still not quite sure I get what it's all about.
In a nutshell, quantum computers use these things called qubits, which are like the quantum versions of the bits in our regular computers.
Okay.
But here's the kicker. Qubits can be in multiple states at the same time, unlike regular bits, which can only be a 0 or a 1.
Wait, so if a qubit can be both a 0 and a 1 at the same time, how do we actually get an answer out of it? Isn't that like asking a spinning coin to land on both heads and tails?
That's a great question. It all comes down to how we measure and manipulate these qubits.
Okay.
It's like taking that spinning coin and forcing it to choose a side, but the way we force it can influence the outcome.
Oh, interesting.
It's complex, but incredibly powerful.
So how do time crystals fit into all of this?
Well, imagine using the persistent oscillations of a time crystal, its ticking, to represent information in a qubit.
Okay.
Because of the way they behave, these time crystal qubits could be much more stable and less prone to errors than other types of qubits.
So time crystals could be the key to making quantum computers more reliable and actually useful.
Exactly. And here's another mind-blowing fact.
Ah.
Google actually used their quantum computer to build a time crystal.
Whoa, really? So we're not just talking about theoretical possibilities here. There are real-world applications already happening.
Absolutely. This is one of the first real-world uses for quantum computers. And it really showed the potential of these systems to create and study exotic phases of matter, like time crystals.
Okay, so you've officially convinced me that time crystals are a big deal. But as with any new technology, I imagine there are some hurdles to overcome.
Of course. One of the biggest challenges right now is that time crystals are incredibly delicate.
Okay.
To create and maintain them, you need incredibly low temperatures, like fractions of a degree above absolute zero.
So to create time crystals, we need temperatures colder than a penguin's flippers in Antarctica.
Right.
Sounds like my kind of vacation.
It's definitely not something you can just whip up in your kitchen.
Right.
So finding ways to make them more robust and usable at higher temperatures is a major focus for researchers.
Okay, so besides the extreme cold, are there any other challenges?
Another big one is figuring out how to perform logic gate operations between multiple time crystals.
Logic gate operations.
Yeah, logic gates are the fundamental building blocks of computers, the ANDs, the ORs, the not Ts, that allow computers to actually process information.
So we need to find a way to make time crystals talk to each other in a way that we can control and understand.
Exactly.
Yeah.
And in the quantum world, this involves manipulating something called entanglement.
Entanglement.
Yeah, think of it like taking two of those spinning coins we talked about and linking them together so that when one flips, the other flips automatically.
Okay, I'm starting to see how complex this is. So the challenge is to find a way to entangle multiple time crystals without messing up their delicate quantum states.
Precisely. It's a big challenge, but if we can overcome it, the possibilities are mind-boggling. We're talking about quantum computers that are exponentially faster than anything we have today.
Imagine the possibilities. Drug discovery, material science, artificial intelligence, all supercharged by time crystal-powered quantum computers. It's almost too much to comprehend.
It really is. Time crystals have shown us that there are phases of matter we never even dreamed of, and this is just the beginning. It makes you wonder what other exotic states of matter are out there just waiting to be discovered.
Yeah, it really is kind of wild to think about. We started talking about crystals that we can hold in our hands, and now we're talking about things that could, like, revolutionize computing.
Right.
And maybe even our understanding of time itself.
Yeah, and that's what I think is so fascinating about them. They're not just like a cool scientific discovery.
Yeah.
They're forcing us to like rethink some of our most fundamental assumptions about the universe.
Yeah, it's like we've always kind of thought about time as this, straight line, always moving forward.
Right.
But now we have these time crystals that seem to have their own internal clocks,
Uh-huh.
ticking away regardless of what else is going on around them.
Yeah, like it's as if they've tapped into this like deeper level of reality where time isn't just this smooth, continuous flow, but maybe it has like a structure.
A granularity that we're only beginning to glimpse.
So maybe time crystals aren't just about, faster computers. Maybe they're like a window into some of the biggest secrets of the universe.
Exactly.
That's
And who knows what other strange and wonderful phenomena are out there just waiting to be discovered.
Right.
I mean, time crystals have shown us that our imaginations are often too limited
Yeah.
when it comes to the universe.
Well, you've definitely expanded my imagination today. We've gone, from their entropy-defying oscillations to their potential to, like revolutionize quantum computing.
Yep.
But I can't help but wonder, like, what do you think the future holds for this field?
Oh, man.
Where do we go from here?
I think the future of time crystals and really the future of physics and technology in general is going to be even more surprising than we can imagine.
Yeah.
I mean, we've only just scratched the surface of what's possible.
And I have a feeling that there are many more mind-blowing discoveries just around the corner.
Yeah, it's exciting to think about. And that's what's so great about doing these deep dives with you,
Yeah.
We get to explore these cutting-edge topics and maybe even spark some curiosity and inspiration along the way.
Yeah, absolutely. And who knows, maybe one of our listeners will be the one to make the next big breakthrough in this field.
Right.
That would be awesome.
That would be amazing. So as we wrap up our deep dive into time crystals, we want to hear from you. What stood out to you from this conversation?
Yeah, what questions are swirling around in your mind?
Do you think time crystals will live up to the hype? Let us know, because we're just as curious as you are to see where this incredible journey takes us.